Welcome to the course on advanced power electronics. So we'll be talking today on resonant inverters. So coming to with the introduction, the resonant inverters are class of electronics converters that are utilize resonant circuit to achieve efficient power transfer, and these are widely used in various applications to convert DC energy into AC energy. And applications of resonant inverters are radio transmitters, solid state electronic ballast for fluorescent lamp, high frequency electronics process, heating applied induction welding, surface hardening, soldering and annealing, induction sealing for tampering proof packages, and fiber optics production, dielectric heating for plastic welding. The resonant inverter can be broadly modified into two types: the resonant series inverters, series resonant inverters, parallel resonant inverters, and series parallel resonant inverters. So coming to first category of series resonant inverters. So these are typically series resonant inverter where we have two devices with the typically two inductor, and then in parallel we have with the negative rail L, C and resistance. The above figures show the circuit diagram of simple series resonant inverter using two unidirectional transistor switches. And these are the typical waveform and getting signal, how we give the getting signal to two devices, then how the current, typically output current goes toward zero, and how the capacitor voltage at the output is really produced. Well, so corresponding now coming to when transistor Q1 is turned on, there is a resonance pulse of current flows through the load, and the current falls to 0 at t equal to T1 amp, and Q is self-commutated. And when Q2 is turned on, it causes reverse resonant current through the load, and Q2 is also self-commutated. So for proper operation of the converter, the series resonance circuit formed by L and C and the load, which is assumed to resistive for the simplicity, must be underdamped. Hence, R square must be less than 4L upon C. So this is coming to now analysis. If we talk about this equivalent to a one source and then a one typical series diode, because current can flow in one direction, and we have a current flowing into through inductor, capacitor, and of course the load resistance. So coming to the mode 1, the Q1 is turned on and the resonant pulse typically flows through the Q1 and the load, and equation is L di1 upon dt plus Ri1 plus 1 upon C under integration I1 dt plus Vc1 at the time equal to 0 equal to Vs, and with the initial condition I1 equal to 0 equal to Vc1 equal to minus Vc. So as discussed in the previous analysis of resonating under the LC circuit, so I1 t equal to A1 e to power minus t upon R upon 2L sin omega R t, and omega R is the resonant frequency, and it is given as omega R equal to 1 upon L in bracket 1 upon LC minus R square divided by 4L square under root, and the constant A1 can be evaluated from the initial condition as di1 upon dt at t equal to 0 equal to Vs plus Vc upon omega R L, that is A1. So now hence the current during this mode is I1 t equal to Vs plus Vc divided by omega R L into e to power minus alpha sin omega R t, where alpha is R upon 2L, and the time when the current becomes maximum can be found from the differentiating the equation of the current and equating to 0. So di1 upon dt equal to 0, or omega R e to power minus alpha tm equal to cos omega R tm minus alpha e to power minus alpha tm into sin omega R tm equal to 0, and from this we get tm equal to 1 upon omega R sin tan inverse omega R upon alpha. So the capacitor voltage can be found by integrating the current during this period and adding the initial capacitor voltage. So Vc1 as a function of t equal to 1 upon C 0 to integral 0 to t I1 t into dt minus Vc, and where Vc1 t equal to minus in bracket Vs plus Vc to power L minus alpha t in bracket alpha sin omega t plus omega R cos omega t divided by omega R plus Vs, and at the end of this mode I1 at the t1 t equal to t1 m equal to 0, so Vc1 at the t equal to t1 m equal to Vc1, and that is equal to Vs plus Vc e to power minus alpha pi upon omega R plus Vs. So now typically coming to mode 2, where we have a inductor, capacitor and resistance, and current to throw that initial 0. So mode 2, in this mode both the transistor Q1 Q2 are off, and the mode ends at the time equal to T2 amp. So I22 equal to 0 and Vc2 equal to Vc1, and Vc2 equal to Vc1, and you have another mode 3 when the typically diode conduct the series RLC circuit. So Q2 is on, and the reverse resonant current flows through the load to L di by 3 upon dt plus R I3 plus 1 upon C integral I3 dt plus Vc3 equal to 0. So with the initial condition I3 equal to 0 and Vc3 equal to minus Vc2 minus Vc1. So solving for the current IC I3t equal to Vc1 upon omega R L e to power minus alpha t sin omega R t, and again the capacitor voltage can be found from integration as Vc3 t 1 upon C 0 to t integral I3 into dt minus Vc1 and Vc3 equal to minus Vc1 e to power minus alpha t in bracket alpha sin omega R t plus omega R sin cos omega t upon omega R. At the end of this mode, I3 equal to 0 and Vc3 equal to Vc equal to Vc1 into e to power minus alpha pi upon omega R. So from the above equations, considering pi alpha pi upon omega R equal to Z and Vc comes equal to Vs 1 plus e to power minus Z divided by e to Z minus e to power minus Z equal to Vs e to power Z plus 1 divided by e to power 2Z minus 1 or equal to Vs upon e to Z minus 1, and Vc1 becomes Vs upon 1 plus e to power Z divided by e to power Z minus e to power minus Z equal to Vs e to power Z 1 plus e to power Z divided by 2 e to Z minus 1 or equal to Vs into e to power 2 divided by e to power Z minus 1, where Vs plus Vc equal to Vc1. So hence the peak value of current in mode 1 and mode 3 will be same, that is the positive and negative peaks are same. So to avoid the short circuit condition, the load current I1t must be 0 and Q1 must be turned off before Q2 is turned on. Hence the dead time to be provided is greater than the turn off time of the switch, that is pi upon omega 0 minus pi upon omega R equal to t, that is greater than t of. So when omega 0 is the resonance, is the frequency of the output voltage in radian per second, and as the maximum possible output frequency limited to f less than or equal to f max upon equal to 1 upon 2 in bracket t of plus pi upon omega R. Now coming to the same series resonant circuit, here we connect a capacitor resistance series from this point. So an improved circuit is obtained by using coupled inductor, and where Q1 is turned on and current flow I1 flow begins to rise and the voltage across L1 positive as shown, and the induced voltage on L2 adding to voltage C turn off the Q2. The above circuit of the series resonant inverter and the power flow from the DC supply is discontinuous. DC supply has a high peak current and will contain harmonics, and the drawback of high pulse current from the DC supply can be overcome in a half bridge configuration. And these are typically half bridge configuration, that where we have a midpoint converter with the resistance in between the midpoint of this coupled inductor with the two transistors. It's called a half bridge series resonant inverter. And when Q1 is on, the circuit becomes typically with the series diode L and R with the midpoint of these two capacitors, which becomes equal to like a supply voltage with the series capacitor equivalent, and then with the L and R circuit with another capacitor in parallel. So when Q2 on, then also the circuit from midpoint R, L and L with the series diode and becomes C1, C2 in parallel with R and L in series, and that becomes finally the capacitor V1 and R and L circuit series. So here L1 equal to L2 and C1 equal to C, considering the loop formed by C2 DC source L and load and applying KVL across it. So it's L diu upon dt plus RIU plus 1 upon 2 C2 integral I0 dt plus Vc2 equal minus Vs equal to 0. So with initial condition I0 equal to 0, Vc2 equal to minus Vc. For an underdamped circuit, I0 equal to Vs plus Vc upon omega RL e to power minus alpha t plus sin omega RT, and resonant frequency is omega R equal to in bracket 1 upon 2 L C2 minus R square 4 L square under root of that, and voltage across the capacitor C2 is Vc2 equal to 1 upon 2 C2 0 to t I0 t dt minus Vc, and that Vc2 equal to minus Vs plus Vc e to power minus alpha t in bracket alpha sin omega t plus omega R cos omega t divided by R omega plus Vs. So in the half bridge configuration, the power is drawn from the DC source during the both half cycle of the output voltage, and one half of the load current is supplied by capacitor C1 and C2 and the other half by the DC source. So for the same output power and resonant frequency, the capacitance C1, C2 of the half bridge resonant inverter is half of the value as compared to the basic series resonant inverter discussed previously, and peak supply current also becomes half. And this is typically a full bridge series resonant inverter, that in between we have RLC, series circuit with the resonant with the full bridge. So the full bridge configuration of the series inverter circuit allows for higher output power as compared to the half bridge configuration. When Q1, Q2 are turned on, a positive resonant current flows through the load, and when Q3, Q4 are turned on a negative load current flows, hence the supply current is continuous but pulsating in nature. The rest of the analysis is similar to the half bridge configuration. So resonant frequency and available dead zone are dependent on the load, and hence the resonant inverter are most suitable for fixed load application. So now coming to typically series resonant converter with bidirectional switches. So for the resonant converter unidirectional switch, the power switches have to be turned on in every half cycle of the output voltage. So this limits the inverter frequency and amount of the energy transfer from the source to load. Moreover, a high peak reverse voltage is applied across the devices, which results in higher voltage stress, and the devices need to be chosen are of high rating, and the performance of series inverter can be significantly improved by connecting an anti-parallel diode across the device. You can just see how really the device you connect, the diode connect across, and then LNC in series, and with the typically of isolant transformer, and you can see how the current and voltage waveform here. So when the switching device Q1 is turned on, a resonant pulse of current flows, and Q2 is self-commuted at T equal to T1. Although the device Q2 is now turned off, the resonant oscillation continues through diode D1 until the current falls again to 0 at the end of the cycle. So if the conduction time of the diode is greater than the turn-off time of the device, there is no need of providing a dead zone, and the output frequency will be the same as the resonant frequency. So F0 equal to Fr equal to omega r upon 2 pi. However, the device requires a minimum finite time for switching. This time consists of delay time, write time, fall time, and storage time. So TSW equal to TD plus TR plus TF plus TS. Thus, the maximum frequency up to which the inverter can operate is given by Fs maximum upon 1 upon 2 TSW. The frequency of the output frequency of 0 should be less than this frequency of S maximum. So for high power converters, if the switching device is thyristor, then any stray inductance due to the internal loop Q1 and D1 should be minimized. So this is required because the reverse voltage during the recovery time of the thyristor is already low, typically 1 volt, and an inductance in the loop reduces the net reverse voltage that affects across the terminals of the thyristor and may not be turned off. To overcome this problem, a reverse conducting thyristor is normally used. So RCT is made by integrating an asymmetric thyristor with the fast recovery diode on a single silicon chip. The typical circuit with midpoint and L and R with the two devices, half bridge series generator with bidirectional switches, and the full bridge with the series generator with bidirectional switches. So you can just see mode of full bridge, and you have typically a series RLC circuit, connected in two different way current flows here with bidirectional switch. So coming to mode 1, the switch Q1, Q2 are turned on, the resonating current start flowing through Q1 and Q2 load and supply, and it becomes LDIO upon dt plus RIO plus 1 upon C integration I0 dt plus Vc equal to Vs, and with the initial condition I0 equal to 0, Vc1 equal to minus Vc. So solving the current, one gets I0 equal to Vs plus Vc divided by omega RL e to power minus alpha t into sine omega RT. So similar to the previous analysis, the voltage across the capacitor can be found by integrating the current. So Vc equal to minus Vs plus Vc e to power minus alpha t in bracket alpha sine omega t plus omega r cos omega t plus Vs, and Q1, Q2 are turn off at t equal to pi upon omega r when initial I1t becomes 0, and at this instant the voltage across the capacitor is Vc1 equal to small vc equal to Vs plus Vc1 e to power minus alpha pi upon r plus Vs. And coming to mode 2, the switches Q3, Q4 are turned on, and a resonating reverse regenerating current start flowing through Q3 and Q4 load and the supply. So it becomes L DIO upon dt plus RIO plus 1 upon C I dt plus Vc equal to minus Vs. With initial condition I2 equal to 0, Vc equal to Vc1. So solving the current, we get I0 t equal to Vs minus Vs plus Vc1 divided by omega t e to power alpha t into sin omega t. The voltage across the capacitor can be found by integrating the current as done in mode 2. So Vc equal to in bracket Vs plus Vc1 e to power minus alpha t in bracket alpha sin omega t plus omega cos omega t divided by omega minus Vs. In Q3 QR turn off at t equal to T1 equal to pi upon omega r when I0 becomes 0, and at this instant the voltage across the capacitor is Vc equal to minus Vc equal to Vs plus Vc1 e to power minus alpha pi upon omega r plus Vs. So voltage Vc1 and Vc1 can express any the terms of supply voltage Vc equal to Vc1 equal to Vs e to power z plus 1 divided by e to power z minus 1. So as compared to the half bridge inverter, the output power in the case of full bridge is 4 times and the device current are twice. So these inverters can be operated in two different modes, non-overlapping and overlapping. And so you can say in typically in non-overlapping mode, the turning on and of the turning off the on of the devices is delayed until the last current oscillation throw has been completed as shown in the above figure. So in a overlapping mode, device is turned on while the current in the device of the other part of the circuit is still conducting. Although this operation increases the output frequency, the output power is also increased. So this is class D voltage source inverter topology. As you can see here, how it is really a half bridge with the supply voltage and with the RLC circuit, which may be a kind of replacement you can do by the connecting a transformer, high frequency transformer in light of that, and with the different circuit concept here like. So the adjoining figure shows the class D voltage source inverter with various regenerating circuit, and all these regenerating circuits are derived from the series regenerating circuit, and all these topology produces sinusoidal voltage output and compatible with the voltage driven rectifiers, and the parts of the circuits can be replaced by a high frequency transformer as shown in the figure. So you can see just like half bridge with the series RLC circuit, and the adjoining figure shows a class D voltage source inverter with two DC voltage sources, and the bottom voltage source acts as a short circuit for the current through the regenerator circuit when the switch is off. And a drawback of this circuit is to that the load current flows through an internal resistance of the DC voltage sources, reducing efficiency. And it's class D half bridge topology with the typically your L and R. So the two independent voltage sources of the previous configuration can be replaced by a two capacitor, and this solved the problem of parallel dissipation in the series circuit, series resistance of the DC voltage sources, but the AC power is still dissipated in the equivalent series resistance of the capacitor. So resonant frequency omega 0 equal to 1 upon omega LC, and the characteristic impedance Z0 equal to under root L upon C, that is equal to omega L equal to 1 upon omega C, and the load quality factor QL equal to omega 0 L upon R, that is 1 upon omega 0 CR equal to Z0 upon R equal to under root LC upon R. So the parameters of series inverter circuit, the unloaded quality factor, that is when the circuit is operated at no load and no load resistance is connected at the output terminal. So Q0 equal to omega L upon R, that is 1 upon omega CR equal to Z0 upon omega divided by R. So here R represents the summation of switch on state resistance, series resistance of the inductor, and the equivalent series resistance of the capacitor. And this resistance is also to be considered in the loaded condition and is generally summed with the load resistance. And here the impedance of the series regenerating circuit, you can clearly see how with the frequency this impedance varies to the quality factor. So reactance of the regenerating circuit becomes 0 and at the regenerating frequency F0. And for F less than F0, the regenerating circuit represents the capacitive load to the switching part of the inverter, and for F equal to greater than F0, the regenerating circuit represents an inductive load. So now coming to operation under short circuit and open circuit condition, the class D inverter with the series regenerating circuit can operate safely with the open circuit at the output. However, it is prone to fail if the output is short circuited and if frequency close to the regenerating frequency. If the load resistance is 0 and the amplitude of current through the resonant circuit and the switches is given as Im equal to 2 V1 divided by under root pi r in bracket 1 plus Z0 I square in bracket omega 0 omega upon omega 0 minus omega 0 upon omega square. So maximum value of Im current occurs F equal to F0 and given by Sm equal to IMR equal to V1 upon pi r, and the amplitude of the voltage across the resonant component L and C are VCM equal to VM, VLM equal to IMR equal to omega 0 C equal to omega R, omega 0 L IMR equal to Z0 IMR equal to 2 V1 Z0 upon pi R equal to 2 V1 Q upon pi. So for example, if V1 is Vi equal to 320 volt, R equal to small r equal to ohm, ISM equal to IMR equal to 102 ampere, and VCM equal to VLM equal to 80 kilovolt. So thus the under short circuit condition near the resonant frequency, excessive current in the switches and the resonant circuit as well as excessive voltage across L and C can damage the inverter. So now coming to voltage control of series resonant inverter. Here the bridge is there and you have a series RLC circuit. So normally for the output voltage control, the quasi-resonant inverter circuit shown in the above figure is used, and you can see how the typical the voltage of series resonant inverter looks like. So in this circuit, the switching frequency Fs is taken. It kept constant at the resonant frequency of 0. So by switching two devices simultaneously, a quasi square wave as shown in above figure can be obtained. So Vi equal to 4 Vs upon under root pi, under root 2 upon pi into pi, so it's cos alpha. And the quasi-resonant inverter can be considered as a hybrid of resonant inverter and pendulum inverter. And in this circuit, the power switch is in pendulum inverter is replaced with the resonant switch, and the switch current or voltage are forced to oscillate in a quasi-sinusoidal manner. So by doing so, large family of the conventional inverter circuits can be transformed into their resonant converter counterpart. Now coming to frequency response of the series resonant inverter, by varying the switching the output voltage can be varied. There are three combination of load series parallel and series parallel. And coming to the typically series loaded inverters, so frequency response there, the input voltage, you can see a circuit with L and C R, and where typically are plotting the voltage typically across the inductor Vi and the source voltage. So input voltage is a square wave whose peak component is Pi equal to 4 Ps upon pi equal to Vi equal to 4 Vs upon under root 2 pi. So G as a function of j omega equal to V0 upon j omega by Vi equal to 1 upon 1 plus j omega r upon L minus j upon omega Cr. So where omega 0 equal to 1 upon LC be the resonant frequency and Q equal to omega 0 LR to be the quality factor. And you can see the frequency response for different quality factors, with the frequency variation and the gain. So GW equal to V0 upon Vi as a function of J, and that is equal to 1 upon plus JQS in bracket omega 0, omega equal to omega by omega 0 minus omega 0 upon omega, and that is equal to 1 upon 1 plus JQS in bracket U minus 1 upon U, where the U equal to omega upon omega 0, the magnitude of G can be found from G equal to 1 upon in bracket 1 plus QS square in bracket U minus 1 by U square. So now come square root, and then coming to frequency response of parallel loaded inverter. So you can see how the capacitor connected in parallel to the resistance and series inductor. So here your G equal to VO upon Vi, J function j omega equal to 1 upon 1 minus omega square LC plus j omega L upon R, and where omega 0 is equal to 1 upon LC and Q equal to 1 upon QS equal to R upon omega 0 L. And you can see typically the frequency response for different quality factors. So G upon G equal to V0 upon Pi and equal to 1 upon in bracket 1 minus omega 0 omega upon omega 0 square plus j omega 0 upon omega 0 divided by Q, that is equal to 1 upon 1 minus U square plus j U on Q, where U equal to omega 0 upon omega 0, the magnitude of G can be found out. G equal to 1 upon 1 minus U square plus U upon Q square, under root of that. And coming to frequency resonance of parallel loaded inverters, so with the C and L and capacitor in parallel, so G equal to V upon Vi equal to 1 upon 1 plus Cp upon Cs minus omega square LCP plus J omega L upon R minus J upon 1 divided by omega CSR, where omega 0 equal to 1 upon L Cs and QS equal to omega 0 L upon R. And this is the typically frequency response of series with the 4 different Q for Cp, Cs equal to Cp. So here G equal to V0 upon Vi equal to 1 upon 1 plus Cs upon Cp upon Cs minus omega square L Cp plus J Q in bracket omega 0 omega upon omega 0 minus omega 0 divided by omega equal to 1 upon 1 plus Cp upon Cs 1 minus U square plus JQS in bracket U minus 1 upon Q, where U equal to omega 0 upon omega divided by omega 0. The magnitude of G can be found out. G equal to 1 upon divided by in bracket 1 plus Cp upon Cs minus into 1 minus U square to square of that, and then Q square U minus 1 upon U square and under root of 4. Now coming to parallel resonant inverters. So parallel resonant inverter, you can clearly see where in the inductor and capacitor comes in parallel to the load resistance, and you can see clearly how the typically the voltage and current waveform are there. The current typically voltage becomes sinusoidal, where the current is applying KCL to the whole circuit, C dV upon dt plus V upon R plus 1 upon L indication of VDT equal to IS, and with initial current is V equal to 0, IL equal to 0. So the analysis is very similar to series resonant inverter circuit. The equation of the voltage is then obtained V equal to IS upon omega RC to power minus alpha T sin omega RT, and where alpha equal to 1 upon 2 RC. The damped resonant frequency omega RC is given omega R equal to in bracket 1 upon LC minus 1 upon 4 R square C square root of that, and the voltage becomes maximum at the time Tm equal to 1 upon omega R tan inverse omega R upon alpha, and the input impedance is given by Z equal to V0 upon I equal to R 1 upon 1 plus JR upon omega L plus J omega CR, where I is the input RMS AC RMS current and II equal to 4 pi upon root 2 pi, and the quality factor is considered QP equal to omega 0 CR equal to R upon omega 0 L equal to R under root L C upon L equal to 2 delta, where the delta is a damping factor, delta equal to alpha upon omega 0, and that is equal to R upon 2 into under root C upon L, and the impedance can be expressed as Z equal to V0 upon I equal to 1 upon 1 plus QP in bracket omega 0 upon omega 0 minus omega 0 divided by omega equal to 1 upon plus 1 plus JQP in bracket U minus 1 upon U, where U is equal to omega 0 upon omega upon omega 0. So this is a parallel resonant circuit where capacitor is connected parallel to typically the transformer, and we have a inductor in the input like to make it a current source like. While parallel inverter is the dual of series inverter, it is supplied from a current source so that the circuit offers a high impedance to the switching current. So inductor L acts as a current source, and the capacitor is the resonating circuit, and Lm is the mutual inductance of the transformer act as a resonating circuit. So you can say equivalent circuit with the current source. You have R, Lm and capacitor in parallel, and where the gating signal typically are shown here for VG1, V2. And here you can see how the devices are connected, how the inductor capacitor and another capacitor for the transformer C is equivalent connected with the resistance. The DC blocking capacitor C prevent the DC current flowing through the load resistance. High frequency transformer can also be placed after the resonant circuit in parallel, resonant capacitor in parallel, and these are typical waveform for class D parallel resonant inverter, how they look like and how the zero current and zero voltage. So waveform indicating operation of class D parallel resonant inverter, and these are typically the impedance characteristic, with the quality factor and frequency. So the reactance of the resonant circuit becomes 0 at the resonance frequency of F0. So for F equal less than F0, the resonant circuit represents the capacity load to the switching part of the inverter, and for F equal to greater than F0, the resonant circuit represents an inductive load, and the corner frequency, that is under the neutral frequency omega 0 equal to 1 upon L under root LC, and characteristic impedance Z0 equal to under root L upon C equal to omega 0 L equal to 1 upon omega 0 C. The load quality factor QL equal to omega 0 C Ri equal to Ri upon omega 0 L equal to Ri upon Z0, and the load quality factor at resonance frequency FR equal to FR, that is QR equal to omega R upon L upon RS equal to 1 upon omega R CS as RS, So frequency FR from the boundary condition between the inductive and capacitive load to achieve high efficiency and reliability, F should be higher than the FR under all operating conditions. So FR equal divided by F0 equal to under root 1 minus 1 upon QL square, where QL is greater than 1. Now coming to numerical example. With the numerical example 1, consider the basic series inverter circuit L1 equal to L2 equal to 50 microhenry, C equal to 6 microfarad and R equal to 2 ohm. The DC input voltage is 220 volt. Frequency of the output voltage is 7 kilohertz. The switch turn off time is 10 microsecond. Determine the available circuit turn off time, the maximum permissible frequency, the peak to peak capacitor voltage and peak load current. So resonant frequency, angular frequency omega R equal to in bracket 1 upon LC minus R square 4L square under root of 4, that comes 50,160 radian per second, and hence the resonant FR equal to omega R upon 2 pi, that becomes 8,620 hertz. The available circuit turn off time should be greater than the turn on time of the transistor, so that is pi upon omega 0 minus pi upon omega R, that is T must be greater than T of, so TF equal to pi upon 43.982 minus pi upon 54.9, that becomes 13.42 microsecond. The maximum possible output frequency is limited to F0 must be left F max, that is 1 upon 2 T of plus pi upon omega R, so that is F max, putting a value comes 7,352 hertz. The capacitor voltage VC equal to Vs upon e to power alpha pi divided by omega R minus 1, so putting a value it becomes 100.4 volt, and that VC1 220 plus 104, that becomes 320.4 volt, and VPP that your same 100.4 plus 320.4, that is 420.8 volt. The peak load current occurs at Tm equal to omega R 10 inverse omega R upon alpha, putting a value it comes 22.47 microhenry, and I1 equal microsecond, and I1 equal to Vs plus Vc divided by omega R e to power minus alpha t sin omega RT, and I1 equal to Ip, that putting a value it comes 70.82 ampere, and has the peak value of the load current is 70.82 ampere. Example 2, in a half bridge series resonant inverter, the frequency of the output voltage is 7 kHz. If C1 equal to C2 equal to C equal to 3 microfarad, L1 equal to L2 equal to 50 microhenry, R equal to 2 ohm, and supply voltage 220 volt, determine the resonant angular frequency, the peak supply current, and the resonant angular frequency omega R equal to in bracket upon 2 LC 2 minus R square upon 4L square and root of that, and putting a value it comes 54,160 radian per second. And since the resonant angular frequency is same as the previous example, the equivalent capacitance is equal to C1 plus C2, that is 6 microfarad, and the peak load current is also similar to, that is 70.82 ampere, and the peak supply current, which is half of the peak load current, that is IP equal to 70.82 divided by 2, so that is 35.41 ampere. Now coming to example 3, the considering the circuit of half bridge series resonant inverter with bidirectional switches with no load resistance connected, the frequency of output voltage is 20 kHz, and C equal to 2 microfarad and L equal to 20 microhenry, and supply voltage 220 volt. Supply switching time of the transistor is 12 microseconds. So determine the peak supply current, average device current, and RMS device current. So when Q1 is on, turn on, so the equation becomes TIO DIT upon dt plus 1 upon integral I dt plus Vc equal to Vs, and with initial condition I0 equal to 0, Vc equal to 0. So solving the current I0 equivalent Vs under root C upon L sin omega t, and capacitor voltage is then described as Vc equal to in bracket Vs minus cos omega rt, and resultant frequency omega R equal to 1 upon LC. So from this omega R comes putting a value 158,114 radian per second, and FR is typically 25.165 kilohertz, and resonant time period is TR equal to 1 upon FR 39.74 microsecond. So half the cycle time T1 equal to TR upon 2, that is 19.87 microsecond. So moreover omega V is equal to V omega T equal to pi Vc1, that is 2 Vs equal to 440 volt, and Vc equal to at omega T equal to 0, that is Vc equal to 0. So peak supply current IP Vs under root C upon L, that is 69.57, and average device current IA equal to F0 0 pi sin IP sin theta d theta, that is IP F0 divided by pi FR. So putting a value it comes 17.6 ampere, and RMS device current is your IR do IP under root F0 T1 upon 2, that is 31.01 ampere. Coming to example 4, for the half bridge series inverter featuring bidirectional switches discussed in the previous example. The output voltage frequency is 20 kilowatt, G equal to 2 microfarad, and R equal to 20 microhenry, and the supply voltage of 220 volt. The transistor switching time is 12 microsecond. Consider R equal to infinity, determine the peak to peak capacitor voltage, the maximum permissible output frequency, and the average supply current. So solution is the peak to peak capacitor voltage is VPP equal to VC1 minus PC, that is 440 volt, and the maximum inverter frequency is given by F max equal to 1 upon 2 TSW, and putting a value it comes 41.67 kilohertz, and at the load resistance is infinite. The average supply current of the converter I is equal to 0. Now coming to example 5. For the half bridge series resonant inverter discussed in the example 2, the output voltage frequency now half 3.5 kilohertz, and if C1 equal to C2 equal to C equal to 3 microfarad, L1 equal to L2 equal to 50 microhenry, R equal to ohm, and supply voltage 220 volt, determine the peak supply current, the average device current, RMS device current. As previously calculated, omega R equal to 54,160, so FR becomes 88,619.9 hertz. So TR equal to 1 upon FR, that is 116 microsecond, and T1 equal to half of this, that is 58 microsecond, and T0 equal to 1 upon 3005, that is 285.72 microsecond. So period of load current is T equal to T0 minus TR, it becomes 169.72 microsecond. So because of D is greater than 0, so inverter would operate in the non-overlap mode. So VC equal to 100.4 volt, and VC1 equal to 220 plus 100.4, that is 320.4 volt, and Tm equal to 1 upon TR omega R, tan inverse omega R upon alpha. So putting value it comes 22.47 microsecond, and I0 equal to Vs plus Vc omega R L into power minus omega T sin omega R T. So and the peak current become IP equal to I0, T equal to Pm, that is 70.82, and the average device current can be found out, that is I equal to F0, 0 to T, I0 T, 8.84 ampere, and device RMS current IR in bracket F0, 0 to R1 I0 T square upon into dt, under root of that 22 equal to 22.05 ampere. Coming to example 6, a full bridge series resonant inverter is operating with a out frequency of 10 kilohertz, if C equal to 10 microfarad, L equal to 27 microhenry, and R equal to 1 ohm. Determine the time when the current attains its peak value. So time at which the current becomes maximum can be found Ti1 upon dt equal to 0, or omega R e to power minus alpha Tm cos omega R Tm minus alpha e to power alpha Tm sin omega R Tm equal to 0. So Tm become 1 upon omega R tan inverse omega R upon alpha, and putting a value, this omega R becomes in bracket 1 upon 2L minus I t square upon 4L square under root. So it becomes 38,845 radian per second, and now alpha is equal to R upon 2L, so it becomes 18,518.52, and hence the time at which the current becomes maximum. So Tm equal to putting a value, it becomes 28.98 microsecond. Coming to example 7, a series resonant inverter with a series load is operating with an resonant frequency of 20 kilohertz while deriving a load of power of 1 kilowatt. If the load resistance is 10 ohm, determine the DC voltage, input voltage, equality factor of if it is required to reduce the load power to 250 watt by frequency control, so that help your mu point A and inductor, the inductor L and capacitor C. So because the resonance mu equal to 1 and G equal to 1, max is 1, so Vp equal to Vi max, that is 4 pi upon pi, and PL equal to P square by 2R equal to 4 square Vs square by 2 R pi square, and putting a value Vs become 110 volt. To reduce the load power by 1000 upon 254, the voltage gain must be reduced to 2 at U equal to 0.8. So putting a value, we get the Qs equal to 3.85, and Qs equal to omega L upon R, so L becomes 306.37 microhenry, and for resonant frequency F equal to 1 upon 2 pi L under root LC, we obtain C equal to 206.7 nanofarad. So coming to example 8, a series resonant inverter with parallel load is operating with a resonant frequency of 20 kHz while deriving a load power of 1 kilowatt. The peak sinusoidal voltage 330 volt, and if the resonant load resistance is R equal to 10 ohm, determine the DC input voltage. Frequency ratio, if it is required to reduce the load power to 250 watt by frequency control, the inductor L and the capacitor C. The peak fundamental component of a square wave is Vp equal to 4 pi upon 4 Vs upon pi, and P equal to Vp square 2L equal to 4 square Vs square 2 R pi square, and putting value Vs come 110, and Vi 4 upon 4 Vs upon pi, that comes 40.06, and quality factor VPVI, that becomes 2.356, and to reduce the power by factor of 4, the voltage gain must be reduced by factor 2. So putting a value 1 minus u square to whole square plus u upon 2.356 square equal to 2 square, that u becomes 1.6923, and q equal to r upon omega 0 L. So subtracting value L become 33.75 microhenry, and resonant frequency of 0 equal to 1 upon 2 pi under root LC. So C we obtain is 1.875 microfarad. Coming to example 9, the parallel resonant inverter delivers a load power of 1 kilowatt at a peak sinusoidal voltage of 170 volt and resonance. The load resistance are equal to 10 ohm. The resonant frequency 20 kilowatts, and determine the DC input supply current. The quality factor input is required to reduce the load power to 250 watt by frequency control, so that U equal to 125, the value of inductor, value of capacitor. Because of resonance, U equal to 1 and Z equal to 1, IP equal to 4 S upon pi. So PL equal to IP square R on 2. So from putting a value, we get I is equal to 11.1 ampere. To reduce the load power by factor of 1000 upon 250, that equal to 4. Impedance must be reduced to equal to 1.25. Putting a value in that 1 plus QP square in bracket U minus 1 upon 2 square equal to 2 square, QS equal to 3.85, and QP equal to omega 0 CR, and subtracting value C equal to 3.06 microfarad. And from this resonant frequency of 0 equal to 1 upon 2 pi under root LC, so we obtain L equal to 20.67 microhenry. Coming to example 10, a half-bridge series resonant inverter with bidirectional switches has no load resistance connected to its output terminal. Frequency of output voltage 225 kilowatts, equal to 10 microwatt, L equal to 50 microwatt, supply voltage 110. Determine the expression for capacitor voltage, resonant time period. Resonant frequency is omega r equal to 1 upon omega c, so omega r equal to your 81,649.66, putting the value radian per second. And capacitor voltage then Vc equal to Vs in bracket 1 minus cos omega RT. So Vc putting a value, it becomes 110 minus 3. So we get Fr equal to 81,649.6 by pi. So it becomes 13 kilohertz. So the resonant period is Tr equal to 1 upon Fr, 76.92 microsecond. And these are the references which we have followed to develop this material. And thank you.